Section: Introduction. In this section, we discuss the transformer architecture, which has shown remarkable success in tasks like natural language inference and natural language generation. However, it still operates as a black box, typical of deep neural networks. This has led many researchers to investigate how these models reason internally, aiming to understand their mechanisms. Such research underpins the effectiveness of models like BERT and GPT in practical applications. In today's landscape, where large language models, LLMs, are prevalent, interpretability methods can help us intervene at specific points during LLM inference, improving their problem-solving abilities. Attention heads are vital components in ILM's reasoning processes, and they have received considerable attention recently. We aim to consolidate existing research on attention heads, analyzing their various functions and summarizing the methodologies used in these studies. Our paper is structured logically, as illustrated in our accompanying figure. We start with the background of the problem, providing a simplified view of LLM structures and defining key terms. We then summarize the 4 stages of human thought processes from a cognitive neuroscience perspective and apply this framework to analyze LLM reasoning mechanisms. Using this classification, we categorize existing research on attention heads, highlighting similarities among heads that support similar reasoning processes and examining how heads collaborate across different stages. To understand the internal workings of these models, we recognize that extensive experiments are often necessary to validate hypotheses. We summarize the current experimental methods for studying attention heads, dividing them into 2 categories: those that require additional modeling and those that do not. We also compile evaluation tasks and benchmarks from relevant studies and explore the mechanisms of feed-forward networks and mechanical interpretability to enhance our understanding of LLM structures. We note that, to our knowledge, no survey specifically addresses the mechanisms of attention heads in LLMs. Previous surveys have focused on non-transformer architectures or older attention computation methods, which may not be relevant to current LLMs. Our work stands out by focusing on the latest research, presenting an innovative 4-stage framework for LLM reasoning, and providing a detailed categorization of attention heads based on their functions. We also clearly summarize the experimental methods used to investigate attention head functions, laying the groundwork for future research advancements. This paper primarily targets attention heads within mainstream LLM architectures, particularly those with a decoder-only structure. We do not delve into earlier studies on transformer models, such as those related to BERT. While some studies discuss holistic operational principles, we focus solely on attention heads, briefly summarizing other components in our background section. To facilitate our discussion, we define relevant notations. A model consists of an embedding layer, a series of identical decoder blocks, and an unembedding layer. The input comprises 1 hot sentence tokens, which are transformed through the embedding layer into a matrix for the first decoder. Each decoder block contains 2 residual blocks and multiple attention heads. We will focus on the attention head functions, which involve matrix operations to derive query, key, and value matrices, ultimately contributing to the model's output. Section Summary. In this section, we discuss the significance of the transformer architecture and its attention heads in understanding the reasoning processes of large language models, LLMs. We outline our paper's structure, which includes a classification of attention heads based on a 4-stage framework derived from cognitive neuroscience, and summarize the methodologies used to investigate these mechanisms, emphasizing the need for improved interpretability in LLMs. Section: Glossary of Key Terms. In this section, we introduce several specialized terms related to modeling reasoning mechanisms and exploring experimental methods. We explain key terms as follows. Circuits refer to the reasoning logic in deep models, which we can think of as a computational graph. We can model circuits in 2 ways. One approach treats features in the model's latent space as nodes and the transitions between them as edges. The other approach considers components like attention heads and neurons as nodes, with their interactions, such as residual connections, as edges. A circuit is essentially a subgraph of the model, and current research on attention heads mainly uses the second approach. Residual stream describes the sum of the embedding and outputs from all layers up to a certain layer, which then serves as input for the next layer. We can view the residual stream as a shared bandwidth where different layers can exchange information, with lower layers providing data and higher layers interpreting it. Knowledge circuit is a crucial subgraph that helps us understand how transformers express internal knowledge through the collaboration of different components. Activation patching involves changing the activation values in specific layers to assess their impact on the model's decisions. In contrast, an ablation study removes a component from the model to observe the resulting changes in output. Both methods require us to evaluate the effects on output, which can be categorized into direct, indirect, and total effects. The main distinction is that activation patching modifies values without removing components, while an ablation study logically eliminates a component. The logit lens helps quantify effects by mapping an intermediate representation to the logit values of the vocabulary, allowing us to compare differences in logits or other metrics. In our overview of special attention heads, we note that previous research indicates that the decoder-only architecture follows the scaling law and shows emergent abilities when the number of parameters reaches a certain level. Many large language models, LLMs, demonstrate impressive performance across various tasks, yet the reasons behind their success remain unclear. Recent studies have begun to explore the internal mechanisms of LLMs, focusing on their structure, which consists of multi-attention heads and feed-forward networks. We observe that many studies emphasize the functions of attention heads to explain their reasoning processes, drawing parallels between LLM reasoning and human reasoning. To understand how an attention head thinks, we summarize existing research and find that its role is similar to that of the human brain. From a behavioral neuroscience perspective, human thinking can be broken down into 4 steps: knowledge recalling, KR, in-context identification, ICI, latent reasoning, LR, and expression preparation, EP. These steps can interact and transition among each other. When faced with a problem, we first recall relevant knowledge, KR, then identify the context of the problem, ICI, integrate this information to draw conclusions, LR, and finally prepare to express our answer verbally, EP. These stages are not strictly linear. We can cycle back and forth between them as needed. We will now draw an analogy between these 4 steps and the mechanisms of attention heads, noting that LLMs exhibit strong contextual learning abilities and have various practical applications. Consequently, the functions of known special attention heads mainly focus on the ICI and LR stages, with fewer heads involved in the KR and EP stages. Section Summary. In this section, we introduce key terms related to reasoning mechanisms in deep models, such as circuits, which represent the reasoning logic, and the residual stream, which facilitates information transfer between layers. We also explore the analogy between attention heads in LLMs and human cognitive processes, highlighting their roles in knowledge recalling, in-context identification, latent reasoning, and expression preparation. Section: Knowledge recalling, KR. In this section, we discuss knowledge recalling, KR, in large language models, LLMs. We recognize that most of the knowledge in LLMs is acquired during training or fine-tuning and is stored in the model's parameters, which we call parametric knowledge. Similar to how humans recall information, certain attention heads in LLMs access this stored knowledge, such as common sense or specialized expertise, to aid in reasoning. These heads often make initial guesses or focus on specific content, integrating memory into the processing stream. We observe that some attention heads act like associative memories, gradually storing and retrieving knowledge throughout training. The memory head can pull relevant information from the parametric knowledge, which may include insights gained during pre-training or from past reasoning experiences. In specific tasks, like multiple-choice question answering, MCQA, LLMs might use a constant head to distribute attention evenly across options or a single letter head to prioritize one option over others, capturing all possible answers. In binary decision tasks, BDT, we find that LLMs often show a negative bias, likely due to prior exposure to negative expressions during training. This can lead a negative head to favor a negative answer when faced with a binary task. Next, we address in-context identification, ICI, which is crucial for effectively solving problems. Just as humans quickly identify key information in a problem statement, certain attention heads in LLMs focus on these elements. During the ICI stage, attention heads utilize their QK matrices to identify structural, syntactic, and semantic information, which is then recorded in the residual stream through OV matrices. For overall structural information, LLMs pay attention to content in specific positions or unique occurrences. The previous head, or positional head, tracks relationships between tokens, while the rare words head emphasizes infrequent tokens. The duplicate token head focuses on repeated content, and the global retrieval head helps locate specific tokens in longer texts, enhancing reading and retrieval capabilities. In terms of syntactic information, sentences consist of subjects, predicates, objects, and clauses. The syntactic head identifies and labels these components. The subword merge head addresses cases where words are split into subwords, merging them back into complete words. We also mention the mover head cluster, which acts like argument parsers, transferring important information to the end position. The name mover head and backup name mover head relocate names, while the letter mover head gathers initial letters of certain words. Conversely, the negative name mover head prevents name information from being moved. Finally, for semantic information identification, the context head extracts relevant information for the current task. The content gatherer head moves tokens related to the correct answer to the end position for output. The sentiment summarizer condenses sentiment-related adjectives and verbs, aiding subsequent reasoning. We also highlight the importance of capturing relationships, with the induction head identifying semantic relationships and the subject head and relation head focusing on attributes to inject into the residual stream. Section Summary. In this section, we explore how large language models, LLMs, utilize various attention heads to recall and identify knowledge during reasoning tasks, akin to human cognitive processes. We detail how these heads focus on structural, syntactic, and semantic information, enabling effective in-context understanding and retrieval of relevant knowledge for tasks like multiple-choice question answering and binary decision-making. Section: Latent Reasoning, LR. In this section, we discuss latent reasoning, LR, which is crucial for synthesizing information and logical reasoning. Both humans and large language models, LLMs, rely on this stage for problem solving. Here, QK matrices in a head perform implicit reasoning using data from the residual stream, and the results are then written back into this stream through OV matrices. Next, we explore in-context learning, which includes task recognition, TR, and task learning, TL. While both types learn from context to solve problems, TR uses clear semantic labels, like positive or negative, in sentiment analysis. TL, on the other hand, focuses on learning the relationship between examples and labels that may not have a semantic link. For TR, a summary reader can utilize summarized information to determine sentiment labels. We propose that certain mid-layer attention heads can create a function vector that captures essential features and relationships of a task, triggering its execution. For TL, the goal is for LLMs to identify patterns inductively. The induction head is a key attention head that recognizes patterns, such as when one token follows another, and predicts the next token accordingly. It gathers information from all tokens in context and uses it for reasoning. However, real-world problems often differ from examples, similar to how a student's exam may not mirror their homework. To tackle this, we introduce the in-context head, which assesses the similarity between the information at the end position and each label, allowing for a more comprehensive answer by considering all labels. We also identify heads that enhance reasoning effectiveness, such as the truthfulness head and accuracy head, which help ensure correct answers in question-answering tasks. However, some heads, like the vulnerable head, can be overly sensitive to specific inputs, leading to errors. We recommend minimizing their influence during reasoning. In the expression preparation (EP) stage, LLMs align their reasoning with verbal expression. EP heads aggregate information from various stages, and we propose the mixed head, which combines data from ICI and LR stages. Some EP heads amplify signals, ensuring that the correct choice in multiple choice questions has the highest probability after processing. Additionally, EP heads help align reasoning with user instructions, maintaining linguistic consistency in multilingual tasks through the coherence head. The faithfulness head enhances the alignment of internal reasoning with outputs, making results more robust. However, for simpler tasks, LLMs may skip the EP stage and directly use the most probable token from the residual stream. Section Summary. In this section, we explore the latent reasoning (LR) stage, where collected information is synthesized for problem solving, and discuss in-context learning (ICL), which includes task recognition and task learning, highlighting their different approaches to inferring solutions. We also examine the roles of various attention heads in enhancing reasoning effectiveness, expression preparation, and ensuring coherence and faithfulness in outputs, while noting that some tasks may not require extensive refinement in language expression. Section: How attention heads working together. In this section, we explore how attention heads work together in a language model, like GPT-2 Small. We categorize the model's layers into 3 groups: shallow, layers 1 to 4, middle, layers 5 to 8, and deep, layers 9 to 12. This helps us understand how attention heads interact within these layers. Some researchers have looked into the meanings behind the query and key vectors when heads collaborate. For instance, in a multiple-choice question scenario, during the initial content identification stage, a content gatherer head moves the correct answer to the end position. Later, in the label recognition stage, a correct letterhead uses this information to find the right option, asking, "Are you the correct label?" while recalling the gathered answer. The key vector indicates the choices available. By matching the query and key vectors, we can identify the correct answer. In the parity problem, a mover head sends the position of a token that separates the input from the intermediate state to the end position. Then, an iteration head checks this position, asking, "Are you position T?" Each token responds with its position, helping the model determine the last digit in the input sequence. We also investigate how multiple special attention heads can work together. For example, in the indirect object identification task, the subject head and relation head focus on key elements in a sentence, leading the model to recall that the answer is a person's name. During the content identification stage, a duplicate head identifies John, while a name mover head focuses on both John and Mary. As the process continues, the previous head and induction head collaborate to attend to John, and the inhibition head suppresses its logits value since John appears multiple times. Finally, the amplification head boosts the logits for Mary. To uncover the specific functions of these special heads, we primarily use experimental methods. We categorize these methods into 2 types: modeling free and modeling required. Modeling free methods do not need new models and are widely used in interpretability research. They typically involve changing a latent state during the reasoning process and using logit lens to connect the results to token probabilities. By analyzing the differences in logits, we can infer the effects of these changes. Modeling free methods include activation patching and ablation study. We further divide these into modification-based and replacement-based methods. Modification-based methods change specific latent state values while keeping some original information. For example, we can analyze sentiment by adding or removing sentiment direction vectors to see how it affects the output. On the other hand, replacement-based methods replace all information in a latent state with new values. Zero ablation and mean ablation replace the original state with zeros or the average value from a dataset, respectively, allowing us to assess the importance of specific heads. Naive activation patching replaces the original latent state with one from a corrupted prompt, helping us identify which heads focus on names based on their impact. Section Summary. In this section, we explore how attention heads in a language model collaborate across different layers to perform tasks, such as identifying correct answers or positions in sequences, by utilizing query and key vectors. We also discuss methods for uncovering the specific functions of these heads, categorizing experimental approaches into modeling free and modeling required, with a focus on techniques like activation patching and ablation studies to analyze their impact on model outputs. Section: Modeling Required. In this section, we discuss modeling required methods, which involve creating models to better understand the functions of specific heads in language models. We categorize these methods into two types: training required and training free, as outlined in a table. Training required methods need us to train new models to investigate their mechanisms. A common approach is probing, where we extract activation values from different heads and classify them, training a classifier to learn the relationship between these activation patterns and the head's functions. This trained classifier can then identify which heads in the language models have specific functions. Another method involves training a simpler transformer model on a clean dataset for a particular task. We check if the heads in this simpler model show certain functionalities, which we can then apply to the original model. This approach is cost-effective and keeps the model simple and manageable. Training-free methods focus on creating scores that represent specific phenomena. These scores act as models that establish a relationship between component attributes and model behaviors. For example, when looking at retrieval heads, we define a retrieval score, which measures how often a head gives the highest attention score to the token it wants to retrieve. A high score indicates a strong ability to find specific information. Similarly, for negative heads, we introduce the negative attention score, which shows how much a head focuses on negative tokens during decision-making. A high score here suggests a tendency to generate negative signals. We also explore other innovative training-free methods, such as the information flow graph, where nodes represent tokens and edges show information transfer between tokens through attention heads or feed-forward networks. By assessing the importance of each edge, we can create a subgraph that represents the main reasoning mechanism of language models. Next, we summarize the benchmarks and datasets used in our interpretability research of attention heads. We categorize these evaluations into mechanism exploration evaluation and common evaluation. The first type assesses how specific attention heads work, while the second examines whether modifying certain heads can enhance the overall performance of language models. For mechanism exploration evaluation, we note that many researchers have created new datasets based on existing benchmarks, simplifying problem difficulty and standardizing unrelated elements. These datasets primarily evaluate the model's reasoning and recall abilities, reducing answers from paragraph level to token level. For instance, when exploring sentiment-related heads, we develop datasets like Toy Movie Review and Toy Mood Story, allowing us to analyze activation differences for positive and negative sentiments. In common evaluation, our goal is to improve the overall capabilities of language models. Researchers often modify heads with specific functions to see if this leads to more accurate and useful responses. We classify these benchmarks based on their focus, which includes knowledge reasoning, sentiment analysis, long context retrieval, and text comprehension. Lastly, we summarize various works related to the interpretability of language models. While these studies may not introduce new special heads, they explore the underlying mechanisms from different angles, focusing on FFN interpretability and machine psychology. We highlight that feed-forward networks, FFNs, play a significant role in the reasoning process, storing knowledge from pre-training and collaborating with attention heads. Research shows that knowledge is often concentrated in a few neurons, with a hierarchical storage system in FFNs. This collaboration enhances the overall capabilities of language models, allowing them to explore information both broadly and deeply. Each component of language models is crucial in the reasoning process, and their interactions facilitate the entire process from knowledge recalling to expression. Section Summary. In this section, we categorize modeling required methods into training required and training-free approaches to analyze attention heads in LLMs, with training required methods involving model training to explore head functions, while training-free methods utilize scores to reflect specific behaviors. We also discuss evaluation methods for understanding these mechanisms, including mechanism exploration evaluation for internal reasoning and common evaluation to enhance LLM performance, alongside insights into FFN interpretability and their collaborative role with attention heads in knowledge retrieval. Section: Machine Psychology. In this section, we explore the concept of machine psychology, which connects the reasoning processes of large language models, LLMs, with human thinking. This highlights the need for a unified framework that links LLMs to human cognition. Machine psychology investigates the cognitive activities of AI using psychological theories. Recently, researchers have proposed various methods to study this field. For instance, Hagendorf focuses on applying psychological techniques to uncover new capabilities in LLMs, such as their heuristics, biases, social interactions, language comprehension, and learning abilities. His findings indicate that LLMs exhibit cognitive patterns similar to humans, which can enhance our understanding of AI interpretability and effectiveness. On the other hand, Johansson combines operant conditioning principles with AI, stressing the importance of adaptability and learning from interactions with the environment. This approach aims to address gaps in artificial general intelligence research by merging insights from psychology, cognitive science, and neuroscience. Overall, machine psychology offers a fresh perspective for analyzing LLMs, suggesting that psychological experiments and behavioral studies could reveal new insights about these models. As LLMs are increasingly utilized in various sectors, understanding their behavior through a psychological framework becomes crucial, providing valuable knowledge for creating more advanced AI systems.